Right. A very good morning to all of you. I am now going to make a presentation on green pelletization. And I am sorry for the small delay that took place because of some technical problems. Okay. So, agglomeration as such has been known over centuries. And anybody who walks across an Indian village will see a lot of the discs pasted on the walls of cow dung. And agglomeration has been there in existence, mostly for making use of the finer material, then add a little bit of water, and then make them into something which you can mold into a disc or a roll or whatever it is, pellets. Okay. So now, if you look at the agglomeration process, as I said earlier, any fines can be improved in its size, increased in its size, and can be made use of. The purpose to which the agglomeration is made, or agglomerates are prepared, can be different depending on who is doing and for what he is doing. So the agglomeration has been a very useful process for utilization of materials which are finer and normally not in a position to be used. So if you look at the advantages, you can store them properly once they are increased in size. You can transport them with ease. You can handle them. You can consume them and also put them to use in whatever manner you would like to. So agglomeration has solved many problems, and in the present minerals and metal sector, if you look at it, it is solving the problem of very fine material, slimes, and ultrafine materials, which are invariably generated in a mining operation or a mineral processing domain. So there are two processes which normally are practiced, although there are many, like your briquetting process was the first among the agglomeration processes that were used, followed by nodulizing. The two processes slowly started going away from the scene because they cannot be manufactured on a much larger scale. And as the volume of the fines started increasing, your briquetting press or the nodulizing units will not be able to handle the capacities that we were looking for. So the two processes which at the moment are universally used across the globe are sintering and pelletization. And as you all know, sintering is a process where you heat it to just below the fusion temperature or melting temperature, and then the incipient fusion on the surface of the particles bind them together. So you produce a sinter. The difficulties or limitations of a sinter is that the shape is not of any regular shape, a lot of irregular shape. You need to break them at some point of time to send it to a blast furnace operation. And the permeability that a sinter makes may not be completely conducive to the heat reactions that you need to undergo in the blast furnace. The pelletization gives you an advantage that it produces relatively more regular shaped materials, pellets, which are more spherical, and creates a very good porosity and permeability of the bed so that your reactions are much better and you are able to increase. But the blast furnace feed mix will have to be the lump, sinter, and pellets. Earlier it was only lump and sinters. Now a little part of pellets are also being used. In my opinion, with the kind of the beneficiation processes and the ore that we are mining, the size of liberation will keep going down and down. And then there will be more and more requirement for pellets to be there in the blast furnace mix, feed mix. So once we know that the pelletization is going to be something that has already come to the fore and it will be leading the next few decades, because I have a feeling, personal feeling, that the pellet proportion will increase with the lump and the sinters being relatively, making it maybe another 50% or something. So the pelletization process is carried out in two major events. One is to prepare a pellet which is wet and green and of some size and strength. Later on, you remove the moisture by preheating, then dry it, and then take it to induration before the pellet is ready for being fed to the blast furnace operation. So the green pelletization is the first part, followed by preheating and drying, and then you move to the induration stage. So the production of green balls of a particular size, range, and the strength is of critical importance, because once your green pellets are of proper size and strength, then that leads to a much better indurated pellet in the end. So if I do not have a good vocabulary, then I will not be able to make a good sentence. I mean, taking the analogy. So the green pellets are to be of sufficient size, range, and strength to be amenable for a proper induration, and that should be providing the good blast furnace feed material of sufficient permeability, so that the blast furnace process efficiency is better. So the first step and the most crucial step is the green pelletization. And to all my young friends who are listening to me, like when I started the research on green pelletization, which was my PhD topic in 1981, you can say about 4 decades back. That time also people were saying that why pelletization? Because pelletization has been stopped because of higher cost of fuels in induration. So pelletization has no place, no future. So why you have taken a PhD topic of this nature? But I would give that motivation and confidence to you people that anything that we do is never going to be a wasteful exercise, in the sense that whatever I learned, knowing nothing about pelletization, and I started that in 4 decades back. But then whatever I did during that particular period of about 10 years, when I got my PhD in 87 and later on, and all those knowledge is what I have been making use in solving many pelletization plant operations, in producing pellets of sufficient size, range, size distribution, and strength. That means the knowledge that we gain now may not be immediately of use, but then that knowledge is never going to be an exercise where we fail at any point of time. So a good green pellet produced takes care of most of the downstream processes, in that it will give you a pellet, indurated pellet of good strength and good reducibility in the blast furnace operation. So let us now just take a fundamental look. And this is what I tried to understand in the beginning when I started my career. Why a pellet becomes a spherical particle, and how this process goes on before I get a pellet of a sphere, spherical shape. See, each and every particle, according to its surface area, will have its own surface energy, which could be electrostatic or magnetic or dielectric properties. And they do have a tendency to attract each other. So that will be in a dry state. But then when I add a liquid, the particles and the liquid starts interacting. Then as the space between the two, when water and is trapped between two particles, and when the water starts becoming thinner and thinner, the particles start becoming closer to each other. So when that interfacial area between the two keeps coming down, then the surface free energy that was there keeps also reducing. So the key driving force in the pelletization process, that is green pelletization process, is the shrinking of the interfacial area, which brings the particles together, and then the mechanical action of the rotating device, disc or drum, gives it the final shape. So it is a very good individual microporous, and the pellet will totally have a good permeability there, because it is, so a three-phase system is reduced into a two-phase system. And this is common knowledge. Or it can be a pre-moistened material coming to a pelletizer. Then you add the requisite amount of water in a manner that the water is equitably distributed, so that all the particles have a very good chance of taking the water molecules, and then increase themselves into a size which can be recovered from the disc pelletizer or the drum pelletizer. So a consistent quantity of pellets of sufficient size range, that is 8 to 16 millimeters, is what normally they require, and of sufficient strength, both green compression strength and drop number, will lead to a good drying stage, followed by a good induration stage. So I have just listed the natural forces that make the particles come together and then enable size enlargement. The first one is the van der Waals forces, the magnetic electrical properties, mostly of relevance to a dry state. Then there is second one is the interfacial and the capillary forces due to the action of the liquid, the surface tension of the liquid, and how it binds with the particles together. So that is the force which brings the particles together. The third one is an adhesional or cohesional forces. That is an enabler or an additive, that is binders which give that particular force of bonding together, so that it can increase the strength of the pellet. Then there are solid bridges formed by interlocking. I'm not concentrating because that is very less when it comes to the pellet, but sintering, there will be some amount of interlocking efforts. The final one is the sintering process, infusion and the particles bridge together. So for green pelletization, the three important natural phenomena are the B, C, and D. The solid liquid bridging because of the liquid surface tension and solid surface energy. And then if I add a binder, if sufficient strength is not possible, then the binder gives you the plasticity, flows through, holds the particles more closer and stronger, and gives you a better strength and all. Very minimum amount of interlocking effort. So I would say B and C are the two major forces where the pellets become, the fine particulates become a green pellet. So as I was trying to highlight, it is the interaction between the solid particles and water that really brings them together in the initial stages. So a great contribution from researchers like Ram, Fisher, and Haynes, where they have tried to find out how the three-phase, like solid, water, and air, over a period of time, when it is being rolled together or mixed together, how it becomes a two-phase system. So it goes through a three-stage, like a pendular stage, where you have water in the form of droplets, there are more air pockets, and solids. So the minimum amount of water is holding the particles together. So the pendular bridges will be relatively weaker when you look at the capillary state material. Then when the mechanical force or the applied force starts lengthening the water droplet, the droplet starts becoming lenses. And when it starts elongating, moving through the interstitial spaces between the particles, it starts driving out the air slowly from the system and then occupies that vacuum that is created because of the removal of air. And this process continues till the number of particles which were initially taken by a few droplets, are held together closely, and there is one monolayer of water on the surface of the material. So that particular stage, which we call as capillary, that means all the capillaries have been filled up. So it is completely saturated capillary state material, and that is what we call as a micropellet or a nuclei. These are the ones that have to be formed as quickly as possible, and these nuclei will start interacting with each other, then starts becoming a bigger and bigger pellets there. And that is done by the mechanical action of the rotating devices. And that. We'll come to that. So the capillary state has to be reached in as quick a time as possible. I mean, in the industry, if the nuclei are formed much faster at a very less time interval, then their growth into a final pellet when it is classified out of a disc pelletizer will be lesser than if the nuclei formation starts taking more time and all. I will come to that later when I will share my experiences where how these aspects have been understood and the slight benefits of a continuous pelletization in the industrial scale has been done. A mobile liquid bridging and a binder, if it is added, are the two major bonding mechanisms by which a pendular state agglomerate becomes a capillary state nucleus. This process is what has not been understood in its entirety. Although that everybody knows this is the beginning of the pelletization process, but the sooner it becomes a nuclei and all the dry material in your pelletizer have become some sized nuclei. The size can be anywhere between 0 millimeter to 3 millimeter, 0.1, 0.2 millimeter to 3 millimeter, or even 4. So normally the micro pellets are, let's say, the 3 to 4 millimeter. And that is the beginning of the growth of the pellets before they become more than 8 millimeter, 10 millimeter, 16 millimeter. So the sooner this takes place, the better it is for the pelletization process. So we will see how, what are the different factors that initiate this nucleation and what are the factors that contribute towards the growth and what are the factors that will give the shape and the strength to the pellets that we finally take out from the pelletizing disc or drum. So this again is a force balancing there. In fact, the contribution of Haynes is that he derived a function called suction potential. Is that if there are two particles of a particular surface energy, and if the liquid is holding it together in the form of a droplet when we spray the moisture, okay, the dry particles are attached to the droplets, and the droplet will have to become a lens, and the lens will have to become an elongated material flowing through the pipe, that is the capillary pipe. And then the thinner the water becomes, the better becomes the attachment between the particles and all. So you see going out, that is the expulsion rate of the air, and once that expulsion rate is there, that will be the rate at which the water will become more and more thinner and thinner. And the critical surfaces are under compression. So negative effect of a compression of the solid surface and the removal of water, exudation of water and the air and the water are the two combined forces which bring the particles together. So the disk revolution, the disk inclination, in my opinion, are the two factors that we need to understand for a given feed size distribution, particle size distribution, and for a given moisture content by volume or by weight that we add, what will be the rate at which the water exudation takes place, and how fast it becomes, how quickly it becomes a very thin line, bringing the two particles close together. If that is understood, then the nuclei formation will be under our control. So we need to know the particle size distribution, and according to the particle size distribution, we should find out the critical moisture content that we need to add so that we create a capillary state pellet. Less volume of moisture will create more dry pellets with no strength in it. Or if there is more water, then it will be a floating pellet. So both of them are not good. So those people who have been operating the pelletization plants will suddenly see giant balls coming up. The moisture has not been equitably, so you have more moisture than necessary, and in the process it has dragged all the particles by its side to become something that's bigger, but it is more like a snow falling over a inclined thing. So looks bigger but hollow inside. It doesn't have much strength there. So the giant pellets are because of the floating effect. So this particular figure, I would like to reiterate again that this is how the moisture elongates the water droplets and then removes the air and brings the particles together. Then the capillary state is reached. We should understand how this phenomena can be made faster, maximized in less amount of time, so that more nuclei or all the material have been converted into nuclei. From there, the growth starts taking place. So this particular graph or particular figure is what initially I had a lot of difficulty in understanding. But once it was understood, then the external forces can be manipulated in such a way that this phenomena takes place as early and as quickly as possible. So this is again a pictorial representation of what I told already. So there are, in the beginning you look at two particles, then they starts pointing together. Then the moisture that keeps coming to the surface keeps dragging more and more dry particles into it. Then as more and more particles are there, then the interstitial spaces, the water starts moving out. Then finally we end up with all the pores filled with water, the thickness of water on the surface. And then the nuclei has been arrived at. So this nuclei formation should be, industrial practices should be as quickly done as possible. For that, you need to understand the size distribution of the material that we are treating, what is the quantity of moisture that we need to add, and more importantly, how and where this moisture is added in the pelletizer. Okay, so that what, when I start talking about the factors affecting pelletization, I will come to that. Now, in summation, these are the major activities. Like you have a nuclei formation, and then the nuclei start colliding with each other, and because of the surface moisture, they stick to each other. The number of nuclei keep sticking to each other, so that slightly increases in size, and the process of nuclei joining together to become a bigger entity is what we call as a coalescence. That means coming together of moist fragments, or I will say moist micropellets. So this activity is the first step in the growth process. Then the mechanical forces, sometimes what is the binding force of the pellet and what is the speed of the disc or drum and what is the inclination. So these two, disc and drum speed and inclination, will have a torque generated, and if that is more than the binding force of the pellet, then the pellet is likely to break when it comes and hits the rim of the pelletizer. So there is a lot of material which may form into a coalesced material and break And then the broken fragments again stick onto the surviving smaller entities. Like, so for example, if there is a 3 millimeter, 4 millimeter, 5 millimeter pellets which are nuclei moving around, they may become 8 or 9, and at some point of time, they may break when they hit because the torch starts coating or collecting on the pellets which are about 5 millimeter or 6 millimeter. So that is the second stage, which in this figure it is not shown. Then the broken fragments, which are extremely fine, layer onto the surviving pellets to grow into a pellet of the desired size and strength. This is a very, you can say, macro imaging of the process. And there are a lot of micro events that take place before the final layered pellets, which is of above 8 millimeter or 9 millimeter, which can go out of the pelletizer, starts arriving at. This particular graph, in 1964, when Professor P.C. Kapoor of IIT Kanpur in the University of Berkeley started doing PhD on pelletization, came out with this landmark graph. Why I am saying it is landmark is because this is the fundamental understanding of a pelletization process, especially the balling process, that one has to understand. Then if these regions are manipulated, he has taken number of drum revolutions on the x-axis and then takes the average diameter of the pellet diameter. So as I was trying to say, the nuclei growth region has to be as small as possible, and then the transition zone relatively greater, but the ball growth region has to be much more. So the sooner that ball growth region we arrive at, that means the pellets have to increase from somewhere around 6 millimeter, 7 millimeter, 8 millimeter to 10, 12 and something. So the sooner we reach almost all the material of a pellet size of 7, 8 millimeter, that is what we call as a ball growth region. And that particular one is of critical this one. You can see here, if I draw that ball growth region line to the y-axis, it is about 8 millimeter or 7 millimeter. So the 8 millimeter size, the sooner that it forms, then the ball growth region becomes more accentuated. So you'll get more yield of the desired pellet size distribution from a pelletizer. So for a given material system and for the moisture that we are going to use, the quantity of water, how it is added and where it is added should result in the minimizing of the nuclei growth region, lessening of the transition region, because transition region will anyway be there. There will be particles breaking and layering onto the surviving pellets. But we should lessen the region so that the ball growth region becomes wider, so that we consistently keep getting more pellets in the size range that we desire to come out of the pelletizer. So this is what he used in developing the kinetic models, explaining the growth kinetics of the pellets. So where he used coalescence, then crushing, layering, the models. We'll come to that at a later stage. So now Capes is another scientist who contributed significantly. Two people, Capes and Dankworth. So they were the ones who initially started modeling along with Professor P.C. Kapoor, and then started giving a quantitative analysis of the processes of nucleation, coalescence, and crushing and layering when it comes to batch, and then also layering when it comes to a final process. But in my opinion, the modeling of the nuclei was included as a part of the coalescence modeling, which I later on, when I studied when I started understanding pelletization. I think a good understanding of the nuclei, that means the quantitative understanding of the nucleation process, is the key. If I have to get more pellets in less number of times, that means the production rate has to be increased. But Capes gave us these three mechanisms. One is to form a nuclei and they combine together. Second is a coalescence crushing layering, and finally the fine powder layers onto that, which Professor Shastri later on, when he was trying to use mathematical modeling of the green pelletization process, and then he used the population balance methodology, where he said, yes, the nuclei is coming, that is the birth, then the nuclei are mixing together, interacting together to become a coalesced pellet. That again is a birth. And a coalesced pellet at some point of time breaks. So that is a death. So the population keeps changing as a function of time, as a function of the drum revolutions or disk revolutions. And then the events he started making it micro events. Like you can see many things, nucleation, then attaching together, crushing, breaking, then abrasion, accretion, abrasion transfer. I mean, once we want to mathematically express, we can assume a number of events there and give a pictorial representation of a mathematical expression. But then, to be very succinct, it is always better to have only three processes when you do a batch green pelletization in the laboratory or initial testing at the pilot scale. Then when we go to the continuous process, then we have a fourth process of layering or snowballing. We will come to that, what we are talking about. Maybe I will show you that. Yeah. Please look at this slide. This is the 4 stages of your material growth into your pellet. So initially nuclei, then a coalesced pellet. Then there is transition region where pellets break and keep layering onto themselves. And then you have a layering or snowballing, which when a fresh feed of very fine size starts coming, then that is when the layering or snowballing effect is taking place. So in a batch process, you have got 3, and in a layering, in a continuous process, industrial practice, you will have all the 4 going together. But the rate at which the nuclei becomes coalesced pellet and the disintegration in crushing layering is minimum, then the coalesced pellet will reach the final capillary state pellet as quickly as possible. So the rate between these 4 mechanisms are the ones that we need to reduce. And for that, we need to understand the material parameters, the machine parameters, and then handle both of them judiciously to give you a final pellet of a desired how starts becoming lens towards more solid particles, and the nuclei, and finally it gives you a capillary state pellet. If this is understood as a function of the feed size distribution, the moisture content that I add, the binder content that I add, and what is the speed and the inclination of the rotating device I'm using. If those things are in our hand, but if I understand this mechanism as to how this takes place, then this can be created more efficiently with the understanding of the other parameters which contribute to this phenomena taking place. So these 6 stages of a ball formation and growth is what one has to understand with respect to the material that I am going to pelletize and the kind of binder that I am going to use and what will be the water quantity and how I add it to the pelletizer and what binder I use and how much I will. So all these factors contribute to an early formation and a healthy growth of the pellet in a short duration of time. So this whole activity will need to be done with the understanding of these factors which contribute to the pellet of a particular size distribution and strength. So you can see straight at the bottom and at the top, these two are the critical parameters. That's why I have given them the initial feed size distribution is the starting point of pelletization. And the moisture that I add to this is a function of the size distribution of the feed that I'm going to use. So the interaction between the quantity of water I add vis-a-vis the size distribution of the feed material, these two are the ones that create that nuclei, create that capillary state pellet and all. The binder is an additive that supports the process of nuclei formation. If the pellets that we make out of only water and solid particles are not strong enough to withstand the fall or the impact. So the binders are essentially added. If I don't need to add, I'll be more happy. Okay, so people are also trying to find out whether the feed material itself can be impregnated with a material which has the inherent binding property, then I don't have to add any binder externally. These are all in the laboratory investigation stage, so when it will reach the commercial stage, we don't know. But then if your feed material has a material which has an inherent binding property, then you need to be very careful in what is the quantity of moisture that we add. During my PhD work, I had to use two material systems, and then the manganese concentrate that I produced were becoming very good pellets the way I was following the procedure. The moisture requirement was somewhere around 10.5 to 12. So that is the range at which the pellets were becoming bigger pellets of what I can consider as above 9 millimeter. But when I started using a material called pyritiferous shale, then we thought it contains only a sulfur and then the shale material, a bit of pyrite and this. Then we kept doing the same experiments at the same level of parameters that we were using for the manganese pelletization. Then we were seeing that by the time it is coming to 7 or 8, there was more of flooding. So the particles were becoming more pasty than really becoming any spherical pellets. And a lot of stickiness were there. So then we started reducing the quantity of strength and that. Then we need to understand why this pyritiferous shale is not able to take more moisture, one, and then even with the lesser moisture, it is not able to give the wet pellet. It is somewhere in between with no strength. There is a lot of dry material inside, a wet layer covering on that. So the moment you try to do a drop number and all, not even 1 or 2, then it is crumbling. Then we tried to analyze the mineralogy of that material. We found that the pyritiferous shale has illite, which is a montmorillonite group clay material. And clay materials, like your bentonite also is a clay. So it already has in its mineralogy, pyritiferous shale, the illite, where it was taking the initial moisture that we were adding, and then it was exuding the moisture, and that is why the flooding of the surfaces was taking place when we are going beyond 7 or 8% moisture addition. So then we changed the method of moistening. That means we 50% moisture we added before we put that into a pelletizer, and then we added the remaining 50%, then we were able to get the pellet. So that means you are not only initial feed size distribution, also the characteristic of the different minerals present in your feed will contribute significantly to the quantity of moisture that will be needed to saturate a pellet. And then what should be the way, mean and mode of addition of moisture. So this is what we understood during our PhD work and all. The modeling of that moistening, whether it should be pre-moistened, whether the moisture should be added directly into the pelletizer, if it is added into the pelletizer, at what point it should be added and in what form, whether it should be sprayed, whether it should be added in form of drops. I mean, all these things were tried out in different forms and all. But then it gave us the knowledge that look at the feed material in terms of the size distribution and in terms of the different minerals present in them. When it comes to iron ore, you have alumina silica, you have got gypsite, you have got kaolinite. Okay, the gypsite will react to the quantity of moisture that you are adding, whereas the kaolinite will respond differently. So if your mineralogy contains both gypsite and kaolinite, your addition of moisture have to be different. If it is goethite, you have another problem added, because if it is goethite, kaolinite, and or gypsite, then you have had it, because all of them are water absorbing potential material. So the moisture that I add from outside is normally taken by the binder. So they say that the quantity of binder that I add is proportional to the quantity of water that is immobilized. That means the external moisture that is added, the binder, in trying to swell and move through the interstitial spaces and hold the particles together, it will take that equivalent amount of moisture in trying to swell. So that means if there is an inherent water absorbing material or plastic material, then we need to be careful in what is the quantity of moisture that we add. It should be slightly lesser than what we add to a hematite rich material compared to goethite rich material. And also the way in which it is added, the rate at which it is added, place of addition, all need to be adjusted to give a pellet of a desired size and shape. This knowledge, which I gained somewhere around 86, came to my help when an industrial balling circuit had to be optimized to give a consistently 70 to 80% of pellets above the 8 millimeter or 9 millimeter with sufficient strength. Then our analysis showed that they were adding the same quantity of moisture and the same method of adding moisture and places of addition, but the feed that was coming from 2 or 3 different sources. But there was a lot of metallurgical differences in the material that were coming from source 1, 2, 3. So the blending proportions were not there. So they were getting material, and whatever metal was coming, they were trying to pelletize that. So that helped us in trying to say if these pellets are not getting formed, in one batch the pellets are good, in the other batch the pellets are not good. Because the proportion from source B or C, where there is more goethite or more kaolinite compared to more hematite and magnetite. So then they were responding differently to the pelletization. So that is why, in my opinion, the 2 most critical parameters that one need to understand and also control during the industrial scale operation is the understanding of the feed material we are treating vis-a-vis the quantity of moisture that I need to add, and then how much, how, and where I add. These 2 are very, very critical parameters as far as I am concerned, whether it is a batch process or an industrial process. It doesn't matter. Then we come to the time of pelletization. Like all the people, Professor Kapoor, then Capes, Dankworth, all the people have told. These 3 processes of nucleation, coalescence, and crushing and layering. They are all function of time and function of the operating parameters of the disk or drum. So the kinetics of growth from a coalesced state into a final pellet state is what is controlled by the time, the speed, and the inclination. So I can break this into three now: feed material, moisture, and bentonite or binder. These three are factors that influence a dry material becoming a micro pellet as quickly as possible. If we understand the interactions between these three, then we will be able to produce in less time more nuclei. If it is all the particles which are nuclei, much better. But my experience says that up to 85 to 90% of the dry material or pre-moistened material that is coming can be converted into a micro pellet if we understand the feed material, moisture content, and the binder. Then the growth before the pellets leave the pelletizer is what is controlled by the speed, the inclination, and the time that it stays, residence time of the material inside the pelletizer. So that is also in industrial scale operation. Laboratory, we can do a lot of parameters variation. But in the industry, they will not normally vary quite often the inclination. Once the disk inclination is set, or the drum inclination, that won't be changed. The only two things that we can change is what is the residence time of the material, and then speed. The speed will control the residence time, how fast or how slow we are moving the particles within the pelletizer, and how the moisture is equitably distributed and the nuclei grows into coalescence and a capillary state, a bigger pellet. So these can be controlled by the speed and the time. So speed, inclination, and time are the enablers. They are the ones that finally give you a pellet of a particular size distribution and strength. And the prime movers for the pelletization, that is the green pellet production of both capacity and the quality, will be the feed size distribution, moisture, and binder. Okay, so if we understand these things, we can give you the result that we require, or give the result to the industry which they require. So these are all again what I have said. Okay, the pellet quality and quantity we find out in terms of the size distribution as a function of the average size distribution, because we can represent the size distributions as coarse and narrow, or coarse and wide, fine narrow, and fine wide. And in a pelletization operation, we require relatively a coarser size, but a wider size distribution. So the average size of the distribution will give me an indication as to whether I have reached the pellet size distribution that I'm trying to get out of the pelletizer. Then that will tell me when I screen the material if it is a drum pelletizer, and also if I collect the classified pellets that come out of the disc pelletizer, what is the proportion, weight proportion of the material that is above that particular minimum size, like 8 millimeter or 9 millimeter. In my studies and all, I had taken 9 millimeter as the threshold limit. So what is the percentage of material that is above 9 millimeter? Then we try to find out the strength both at the industrial scale and so the drop number, which is a weighted mean drop number, and the compression strength, so that when it is being transported or when it falls from a given height, it doesn't crumble. And then when there are more material pellets traveling on a conveyor belt or a transporting system, the pellets above will be applying the pressure loading, and that pressure loading or compression should not make the particles crumble. So the particle pellets at the bottom should be able to withstand the pressure exerted by the pellets at the top when they are being transported. So these are the 4 parameters of quality and quantity that we normally need to estimate of a green pellet. Then how we calculate the D50 average size? It could be a simple graph drawn cumulative 8% passing against the size. And then when I draw a line at 50% passing size, then the size of the material at 50% passing, that means it is equally distributed, plus and minus. So that gives me the average size, and that gives me an idea about the coarseness or fineness of the material that I am taking out. So why this D50 is important will come later, because in the modeling, most of the cases, because you can't take the entire size distribution into consideration, you need to have a representative size of the distribution which indicates whether your material is coarser or finer. So some people have, they call it median pellet diameter, which is D50. Sometimes you can even take the 80% passing size as the representative material. That is what comes when you go for a blind number. So when you grind the material and all, you take a material and take it to surface area measurement, and whatever number that comes, you take it as blind number. So the blind number gives you an indication of the fineness or coarseness of the material. In literature, in the modeling aspects, most of the time they have taken the median pellet diameter as the indicator of the size distribution. So this everybody knows, the compression strength and this one. This particular table, in fact, I am a very proud owner of this one. I don't know why I did not copyright it. Why I am saying that is that, so this is just what I did during the PhD work, but this is the table that one needs to prepare when you are pelletizing a material of a particular characteristics, and when you are adding or operating the pelletizer, moisture, binder, inclination, speed, time, all these parameters, how they will influence the final pellet characteristics is what this particular table tells. So there were qualitative experiments carried out. Then based on the range of operating parameters, more rigorous statistical analysis was carried out. And then all that F-test and ANOVA. And then finally we arranged in order of significance of the variables. But this was done during 80s, but for only research purpose. But later on, when more and more material systems were studied for green pelletization, under my guidance with more students coming into the stream, we found that this kind of pattern, this kind of order of significance is prevalent in most of the material systems. Maybe the actual values may vary, but the disk speed, which is S, is the most influencing factor. Whereas we were considering as moisture is the most critical one. But then if I add this much of moisture, and if this is the feed size distribution, what is the speed of rotation of the rotating device that I am using, which will make that drop of pellet become a longer, drop of water become a longer length of the water, then how quickly the air is exuded out of the system, and how quickly we bridge the particles together to form the nuclei. And when we kept on doing this one, irrespective of the material, irrespective of the mineralogy of the material, it was manganese, pyritic shale, limestone, iron ore, or any material for that purpose. We did more than about 30-40 material systems. And we found that this kind of understanding of the influence of different parameters on the pellet characteristics that we want to produce is the basic requirement for a consistent pellet production of a particular size, distribution, and strength. Now, this is what I carried forward, this knowledge, wherever I went to understand and improve the pellet production capacities and a quality production of the same amount of pellets. Wherever the problems were, we analyzed the troubleshooting with this particular influence of the variables. So they told us which are the critical parameters that have an effect or bearing on the final pellet size distribution and strength. Now we went back. What is that operating parameters we are handling? What is the material? How we are adding moisture? Where we are adding moisture? Can I change the location? So with that minor adjustments of quantity of moisture added at different places in different forms, did wonders. Because what we were struggling for months together, once we understood this, and over a period of time, like 1 week or so, we kept doing trial experiments and collected pellets and started understanding, used that statistical analysis to arrive at this kind of a main and interactional effect. We knew if I want a pellet of a better size with adequate strength, then it is the moisture and the speed that I need to really look at, because inclination will not be really affecting. But if I want both pellets of bigger size, but of also sufficient strength to withstand the transportation and the discharges, then we found the interaction between the disk speed and disk inclination were extremely important. So then in some places, we even made the industry people change the inclination with the forecasted material that will be coming. Literally what we did was, in the next 1 year, where will be the material coming to the pelletization from their mines. So we characterized that material from different sources. We arrived at this will be the average composition or distribution of the material. And then this is the quantity of water. And then we gave them the software to say that this is the distribution, this is the moisture, and this is how you should add and all. So when this kind of an algorithm was made, fuzzy logic, if this is what is coming, this is what I should be doing. This helped to a great extent in bringing back the operation to the requisite performance in a smaller interval of time. Whereas people in the industry were saying that we are not getting the consistent result. This small understanding from a batch experiment gave us how a mechanism to look at how the industrial scale operations handle and all. There your recycles also will be an issue. So we had to look at the feed, the product, and the recycle. So then we kept understanding by preparing a chart of the order of significance of variables. This was done for a batch process. Similar ones we can prepare for an industrial scale operation. Only thing we need to be careful is that the pelletizer keeps getting a consistent feed size distribution and a consistent feed mineralogy. If that keeps fluctuating over beyond a range, then it is difficult. Maybe you have to troubleshoot and again bring it back. But once this kind of a thing is built into your industrial scale operation, the operator will be easily understanding that if this is the kind of pellet I'm seeing, some pellets are bigger, some dry, some are looking more wet, then he knows moisture has been increased or decreased. Somewhere moisture is becoming more, somewhere it is being deprived. So all those variations we can bring about without much difficulty. So that is why this kind of a chart being prepared is very, very important once we go for a better control on the pelletization operation. Okay, so whatever I told till now is what people understood qualitatively and how that qualitative knowledge was converted to a quantitative device, algorithms, and how they were made use of in understanding and solving problems of the industry. So there are many ways in which you can do the modeling and all. But most important thing that people have done is initially people did about nucleation, all your capillary forces, the different forces and all. That was theoretical. They were more phenomenological. And then the kinetic approach was the one that was initially used from 1960s to maybe about 19, maybe end of 90s or beginning of the 2000, 2005 and all. But then people started understanding that the kinetics vis-a-vis the population balance approach is a much better approach because of some of the shortcomings of the models that were developed using a kinetic approach, theoretical approach, empirical and all. Most of the people are now comfortable with an empirical one where it doesn't bother about what happens inside the pelletizer, but finally it says that if this is the parameters that you use, this is the pellet of these characteristics, I will be getting that. So the response surface is what people have been trying to use more. So these are all only small, whatever I explained, the same thing and all. What is the growth of pellet in terms of number or size as a function of time is what people started doing in the initial part. Then the order kinetics, whether it is a first order growth or a second order growth, was done by a very limited number of people. This also is an important thing that needs to be done at the industrial scale operation, because the rate at which the particles become nuclei, nuclei to coalescence, coalescence to the final pellet is what is to be understood in order to control the pelletization process. So we should know whether it is a fast kinetics or it is a slower kinetics. The growth takes more time or less time. As I told, if it has more inherent water absorbing material, the kinetics will be slower. But if it is a dry material with not much of moisture inherently, then the external moisture is able to do the job and the rate of growth is faster. So the kinetics, order kinetics need to be understood depending on the material that we are using. As I said, if it is goethite rich, we need to care for the quantity of moisture we add, and we have to understand what will be the residence time of the material that we should give for this material to become a pellet of this size. Okay, then the theoretical ones, then empirical one, then predictive models were there, then population balance model. This is where I think Professor Sastry contributed to a great extent, like as I explained. There are some size range or numbers that are born and some sizes and numbers disappear. So the appearance and disappearance kinetics as a function of the operating parameters is what was involved in this population balancing. So I want a population of this nature finally. So this is the population I start with. Then what is the birth and death or appearance or disappearance kinetics that takes place inside the pelletizer? If I understand, then I can have a relationship between the feed size distribution and the product size distribution. So there is a direct relationship. People say that the initial feed size distribution is directly proportional to what final pellet size distribution I will get. If you start with a 45 micron material, average size of the feed, and you can get up to some 13 millimeter, 14 millimeter. But the quantity of pellets that you get 15, 16, 17, 18 will not be that much because your initial size is much finer. If it is 75 micron, maybe I think you can even get 16. But if it is relatively coarser like 150 micron, you may even get pellets of 18 millimeter. So what final pellet size distribution I get is dependent on what initial feed size distribution I start with. So accordingly, I need to manage the black box because I know the feed, I desire the product. So What is to be done in between is the black box approach. That means the empirical approaches, response surface, is only we keep changing the parameters at an optimum range. This is what I am getting. We are not bothering whether coalescence, how much it has taken place, what is the rate. So that is the black box. Then if you fit a small little bit of data and try to understand the rate at which the coalescence is taking place, rate at which the crumbling, crushing and layering, etc., then it becomes a gray. But we need a white box model. And white box models can come only when you go with your knowledge of the batch process, the pilot scale process, and then go and start working in the plant, spend some time in the plant, look at the dynamics and the variability of the parameters in the industrial scale operations, then blend your knowledge, fundamental knowledge, and the industrial practice to come to a solution where you will be getting more consistent quantity of pellets of a desired size distribution and strength. So the next few cases, I will be showing the equations and all. These kinetics of pellet growth, they say it is pseudo first order or second order. That means most of the material systems, they are first order processes, or there is somewhere transition between first and second order. We don't know, it can be 1.1 order, 1.2 or 1.3. But then when you give more time for a material which is inherently moisture based, then it is going up to the second order growth. So this is only an understanding of the material growth kinetics, which will dictate the residence time distribution of the material in the pelletizer. All these equations are there with you. I will not go into much detail here, but what is important is the thought process that went into developing this fundamental. So initially, Professor Kapoor, Professor Shastri and all, they took number of pellets as a function of the drum revolution. They used drum, not the disc. So when the drum revolution is there, what is the number of revolutions of the drum and how they are producing different number of pellets of a size. So the initial size was I, then the final size I require is J. So how your Ni is varying to Nj as a function of time. Initially, Professor Kapoor took the specific surface, this much material in this size range. That means that will give you a specific surface. So as a function of the number of drum revolutions and that. Then he elaborated that more with respect to the moisture content that we are adding. That means how moisture is influencing the surface, specific surface of the pellet that we produce as a function of the number of revolutions, or you can even convert that into time. Number of drum revolutions can be even residence time of the material. So use a number of revolutions or the time, and then find out the rate of change of number or size of pellet as a function of the moisture content that you have added. So this is where the coalescence part comes. The initial understanding of coalescence was as a function of moisture and the material, specific surface that we get of the pellet. Then another next approach was whether this coalescence is random or non-random. And that is where a lot of debates went on. If you can see those literatures around the time, 60s to 70s and all, there were a lot of models developed, papers published where some people said the coalescence is random, and some people said it is random and fixed. Then some people said it is random but time variant. Then some people said it is non-random. But as far as my knowledge and understanding is that it all depends on the kind of material that you are treating. But fixed random has its own limitations, which I have mentioned in the end there. Because it doesn't take the higher moments of the material growth. It has taken a theoretical maximum of the pellet size and the zero revolution. That means initial feed size. It is not taking any cognizance of the variations in the intermediate stages, time intervals, and also you will not be operating a pelletizer infinite time. Up to a particular time, when the material has to leave the pelletizer, at that particular time, what will be your size of the material, or what will be the number of pellets of a given size? That particular aspect is not covered in the equations that Professor Kapoor developed on that. Then the phenomenological model came with where Shastri combined the approach adopted by Professor Kapoor, and Professor Shastri is a student of Professor Kapoor. So he carried forward the work of Professor Kapoor under the guidance of Dr. Fairstone. So they all gave more kinetic equations as a function of time or the number of revolutions of drum, how the pellets vary in their numbers and size, and defined the coalescence rate. So this is the time by which the rate at which the nuclei will become a coalesced pellet. Then probability approach, a factor of probability of how much probability for coalescence, how much probability for crushing and layering, and how these are interrelated to give the variability of the pellet size distribution that we finally get. So the variance of the pellet size distribution at the end will be a function of the initial pellet size distribution and the changes that take place in the time intervals before a pellet is taken out of the pelletizer. So all these approaches gave us a very good understanding about the coalescence process. And Capes and Dankworths contributed significantly in explaining how much of the material which has become a coalesced pellet is likely to crumble, and then how that will be distributed over. The debate went on. Is it the relatively coarser coalesced pellet that breaks, or it is the finer coalesced pellet? Then which material layers on which material? Whether a coarser material layers on the finer, that means it assimilates, gobbles up the finer material, or it is the finer fragments that go and stick onto the surviving relatively coarser material. So this crushing, how does it take place, and how the layering takes place before my final pellet size distribution is arrived at. This many people were not clear during that time. The contribution of Capes and Dankworths is that he took three sizes: the initial size, that is D0. Sorry. Then he took the maximum pellet, that means at the end of the pelletization process. Then he took a median pellet diameter. So he says, if I can understand from 0 to median, beginning to median, then more or less that will be the rate at which the pellets will be forming. After that, there is a probability of the material breaking. That means there is a pellet size up to which no crushing takes place. So one has to determine that size. For example, if a 4 millimeter nuclei is there, that can go up to 6 or 6.5 millimeters, 7. Till such time it will not break. That means the bonding is still strong enough. Okay, so the impact that it makes with the rim or the collision in between does not really break the material. But if it reaches beyond that stage, that means there are a lot of other materials that are added to the size, but the strength of the bonding strength is not there. So the torque is able to disintegrate the bonding that has taken place. So that is the size. Beyond that size, there is a likelihood of material breaking. Okay, if that material breaks, then what will be the extent of fragments that it will form, and how they will really start layering onto the surviving pellet, or how the surviving pellet will assimilate those finer fragments in that. So this particular expression that he has given included all the aspects that one can consider and gave a very good equation which people have now built into an algorithm, into a computer programming, where they can try and find out the size up to which the pellets do not break. After that, how much breaks, how it breaks, and how does it layer onto each other. So these things can be found out from this mechanism. So order kinetics, as I told, secondary. Okay. Now again, I will come back to this graph. Why? Look at the theoretical aspects that we initially discussed about a natural force and the applied force, and how the dry material becomes a nuclei, and what is the kinetics or the quantitative analysis of the coalescence process, crushing, layering, and the layering process. So in the batch also this will be useful, and in the industrial scale operation, the ball growth region is what will give you that kind consistent. So qualitatively, one has to understand this, and for a given material system, quantitatively you need to develop a similar graph for the material system that we are handling. Then we will be able to understand how these zones or regions vary with respect to the operating parameters. Like inclination normally don't vary. The pellet speed, the disk speed, moisture content, binder, where and how we add. So this particular graph for me is something like a Bible. Like if you want to understand the pelletization, do a few experiments there, draw a graph of this nature, then that will tell you this is the pelletizability of the material. Then we have to keep doing experiments there and keep plotting the same thing to find out how much this regional variation that can take place as a function of the operating parameter. Then you optimize. These are the operating conditions at which I get the smaller nuclei region, lesser region of the transition, and more ball growth region. If we understand this graph for our material and for our scale of operation, we can relatively control with some confidence an industrial scale operation. So, okay, this again I will rush through because I don't know how much time I have. How much time is there? Okay. Am I audible? I am able to. Okay, so the predictive modeling is what Professor Shastri did, where you could put, you could put a probability function for pelletization, like coalescence and crushing layering. Then they could predict the size distribution, but that size distribution, prediction of the pellet size distribution was at the batch scale, not at the industrial scale. But then in modeling and in understanding a process, we can borrow a lot of ideas from different places. Like this approach is normally done in a hydrocyclone classification operation in mineral engineering, where as a function of the operating parameters, you keep, and then when you make your x-axis a dimensionless axis, that means I told you how to find out the D50. So for example, if I change the moisture from 10, 10.5 and 11%, let us say, then at 10% moisture, I'll get a size distribution. 10.5, I'll get another size distribution. And 11, I'll get another size distribution. So plot all the three size distributions and find out the D50. So I have now D50 for 10% moisture, D50 for 10.5, D50 for 11%. Similarly, you vary the disk inclination, disk speed, binder content, time of. So all that x-axis parameters, you keep plotting size versus cumulative 8% passing, find out the D50, and then divide that whatever screens you use to screen the pellets. If I take 9 millimeter or 3 millimeter, 6 millimeter, 6 millimeter is the D, then my D50 is 4.5. Then divided by 4.5 will give me the d by d50. So if that d by d50 I plot on the x-axis, then all my number of S-shaped size distribution curves will fall onto one S-shaped curve, which is what we call as the similarity size distribution curve or self-preserving curve. And this will be a characteristic curve for that material under that operating conditions in which you produce the pellets. So similar graphs, self-preserving curves, one can get for different material systems. Okay, please give me some 2 or 3 minutes, I will join you. So I took some moisture. Okay, carrying forward. So this was a self-preserving curve that was prepared for pyritiferous shale. Then this kind of self-preserving curve was prepared for manganese. So you can see the shape of the curve indicates whether it will give you a wider size distribution of pellet or less shape. You can see here. Here there is not much of variation in the quantity of metal and the pellet size distribution, whereas this could give you a relatively coarser but wider size distribution. And then you have an equation of this nature where it is y is equal to 1 minus exponential 0.693 d by d50 to the power m. So once you know this is the relationship between the cumulative 8% passing, that will give you an idea about the yield of pellet that you will get beyond the number and the operating parameters. Then we need to develop a correlation between the D50 and the different variables that we changed, parameters that we changed. So once you get the D50 parameters like that, this is again characteristic of the operating condition. But the curve that was drawn is a characteristic of the size distribution and yield of material I will get as a function of the operating parameter. Now for a new set of experiments, all I need to do is change the value of moisture, change the value of inclination or binder, then I'll get what will be the D50. Then use this D50 in the self-preserving curve equation, then that will give me what will be the cumulative percentage passing of, that is the Y value. From there, I can calculate what will be my yield of pellets above a particular size. So this approach was used in modeling. This was my PhD work. And this can be easily translated into an industrial scale operation. All we need to do is at the industrial scale operation, we need to go and observe the cyclic variation that takes place in the pellet quality and quantity as a function of the operating parameters. Then develop these curves and all, which now the model itself can do that. Your computer programs can develop those self-preserving curves. And from there, they will be able to tell you if this is the operating condition, suddenly the moisture has gone down, then how your yield will be affected. If your bentonite content has gone down or gone up. So this kind of predicting the variation in your pellet size distribution, which can also be extended to the strength of the pellets. So once these kind of model equations are there and computer programming has been done, then if you keep feeding those continuous data regularly, it can tell you the fluctuations that took place in the product quality and quantity throughout that shift of 8 hours or whatever is the duration of the pelletization period. So these kind of predictive models, which were done at the laboratory scale or batch modeling, have been scaled up and then effectively utilized in controlling the fluctuations in the industrial scale operations. So these are all some of the final model equations for green pelletization that people came out with. And any of these approaches can now be included in the computer programming part. Then we can always determine what will be the size of the pellets that we get, and then what will be the yield of product pellets we will be getting. So all this modeling were quantitative analysis of the qualitative understanding of the fundamentals of green pelletization. Now, we quickly, the pioneers keep getting obsolete easily. Like whatever approach Professor Kapoor used, Professor Shastri improved upon it. Then what he did, somebody else did. Then the process of improving the understanding and expressing the process keeps improving with more and more tools available to us. Like here are some of the reasons why one has to go for the new tools of soft computing techniques and all, because many of the deficiencies or inadequacies of the models are that, as I said, white box models is what we want, but we always have a black box or a gray box. Whether we use a kinetic model, whether we use a population balance model, and some other times a lot of assumptions are there which do not make much sense when it comes to industrial scale operation. And also it is very difficult to determine some of the assumptions, some of the parameters. So then the approach that is available to us is either an extrapolation or an interpolation. Like if I had done only 4 levels, 5 levels, 10 levels, okay, the more the parameter levels and more the parameters, then the number of experiments keep going up. Then it becomes very difficult for any researcher to take the entirety. A complex process cannot be explained very simplistically by only a few parameter variations. So soft computing techniques are good in the sense that they can generate a lot of intermediate data on their own. Once we give the trend, so the trend analysis is able to be done by the soft computing techniques. Some of them that I have tried out is we use a genetic algorithm for optimization. So you can go for different methods for different purposes. Like you can classify the material. That means there is segregation that is taking place. Then you can approximate what will be your result of that. So the classification, this one also. And then you have a self-organizing maps. These are all mostly useful to tell you the pictorial representation where the color that you see and the area that the color covers will say that moisture has more influence. This one, the same thing we have converted, but unfortunately, I don't have those self-organizing maps. Where the pictorial representation, the area covered by different colors, which represent moisture inclination. will tell you how the D50 is influenced by moisture, how the D50 is influenced by the speed, etc., etc. So we used the multi-layer perceptron and support vector machine. We use the same batch data, use the genetic algorithm to generate, like I had only data for 27 experiments and 27 into 3 parameters. So something to the tune of 81 or something. Then we generated something like 400 to 500 intermediate data through the genetic algorithm. So now I have the entire range of variation, the exact trend of the curve, as a how pellet size or strength varies as a function of the operating parameters. So using that large number of data, which takes care of the chaos, the imprecise nature of the earlier models, we are able to understand the exact trend. And once that is there, then the mathematical tools can analyze and give you what result they want. Okay, this will skip there. These are all regression equations that were built into, that were given to the multi-layer perceptron and the support vector machine from the basic data that was there earlier. And this is the kind of data that was generated, synthetic data. So like I had only 27, but then I could generate very close to 300 to 400 micro level data that gave a clear trend of the effect of different parameters on the pellet parameters. And then that was used to predict the pellet. A few experiments where the parameters were varied beyond whatever we had done. And then the multi-layer perceptron gave a much better predictive fit than the support vector machine. But that is only with respect to material. In some other cases, your SVM can be better than MLP. It all depends on what your material, what the operation. Why I am saying this is the use of soft computing gave a better understanding of the variations that can take place in the pellet properties as a function of the moisture to the minutest level of variation. We took only 10 or 12 or something. It's only 2% variation. But between 10 and 12, I can have 100 data. So which is a great advantage. And the prediction or the fit becomes much better than the conventional methods of analysis of variance and fitting and all. Your R and R square values will be much, much better. But when we come to the industrial scale operation, as I told, we need to add a third component of the recycle. In the disc pelletizer, you have a variation that takes place, the agglomeration pattern. It is more like a spring actually. In the bottom portion of the pelletizer, when the dry material is there, and when you are adding moisture, your nuclei and coalescence, all those pellets start forming at the bottom. Then the top layer, which is of a smaller circumference, will be slightly bigger pellet, which could be a coalesced pellet. And then again, there is some crumbling and then rearrangement of the pellet sizes. Then once it reaches the top of the spring, then because of the inclination of the drum or the disc, then there is a natural classifying effect, and pellets above a 9 millimeter automatically goes out to the pelletizer. So this is the advantage of a disc pelletizer compared to a drum. In the drum, you need to have a screen to classify the material and then recycle. But still in disc pelletizer also people do that because the pellets that are discharged from the disc cannot be so very well controlled that some amount of finer material also can be coming with the discharged pellet. But in drum pelletizer, you need to invariably have a classifying device, the screening device. So then it moves up and out, and once the pellet reaches the threshold limit, your inclination is set accordingly so that the pellet, once it reaches the coarser size of 9 millimeter or whatever, it will go out on its own. So the dispelletizer has a natural classifying effect, segregation effect of the particles of different size from the bottom to the top of the rim. So once it reaches the rim height, it goes out. So there is a cyclic, you can get a consistent production, that means keep coming, but your sizes will keep varying. So there is a cyclic variation of the size range. That means you can get now 8 millimeter, 10, suddenly 16 again, it may go down to 10. It all depends on how the crushing, layering and final pellets are taking place. You will keep getting different sizes, but your total quantity of material that is coming out will remain same because the feed rate is there, the product rate will be there. Residence time you are able to control more or less. Surging problems are not that much in a balling disc compared to a drum. In the drum, when the material comes back, the layering part and the nucleation. That happens at the beginning of the drum. Then across the drum, you get pellets which are bigger, and the final pellets are screened and they are recycled back. So in an industrial scale operation, if it has to reach a steady state, whatever is the feed rate or the quantity, whatever is the product pellet I am getting in terms of quantity, and the recycle load, all these three have to be kept constant or should be within a range. Then we can say the system has reached a steady state and my balling operation is under control. Any variation in any of these indicates that there is a problem with the pelletizing operation that is going on. So this is what we normally see. That means it takes number of cycles before it will start reaching a steady state, a consistency. This I am taking only with respect to product. You can see the product fluctuates over a range, over a time. But how much time will it take before it will reach steady state? Depends on your kinetics of the pellet growth and etc. But what we want is as quickly as possible, this fluctuation should even out so that I start getting a consistent product and a consistent recycle load, so that my pelletizer is not surprised with either more material or it is starved of material. Both excess or starvation, both are not good for a pelletizing operation. So if I am doing a drum operation, then I need to control the initial stage where nucleation is taking place, that means the feed end, and the recycled material also coming there. So what is the quantity of recycled material coming and what is the initial feed size that will be coming, and that need to be controlled for nuclei to take place, and then it will give you a consistent feed. So this kind of cyclic variations are what we require so that it becomes steady state as quickly as possible, so that I can control the process without much fluctuation. These are possible, but only if we have understood the fundamentals, the impact of the different parameters, and which parameters are critically important, which parameters are of not that criticality. So this particular graph, again, I don't have much time to explain this one, but again, as Professor P.C. Kapoor's graph, generated graph, this graph is again very, very important, because you can see here, it shows you 4 different curves. One is the feed size that is coming. The one is the recycled material that is going back. One is the product. Okay. And one is the layered pellet. That means many people do not know the nucleation coalescence process. In a continuous operation, the feed material of 150 micron that is coming regularly. In the first stage, that 150 micron became 9 millimeter or 10 millimeter and all. Anything less than 9 is being recycled. Now, when the material of recycle load comes and you have a speed of 150 micron is coming. So how much of this minus 150 micron is layering onto the recycled pellets, or how much of that 150 micron feed is going through the nucleation coalescence process? It will be very good if most of the material that of 150 micron that I am adding, if that layers onto the survived pellet, like recycled pellets, and they reach the pellet size, final pellet size quickly, then that is very good for the plant operator. But if the proportion of layering of the recycled pellets is less compared to the feed size going through a nucleation and coalescence, then our product pellets consistency, the yield will go down. Maybe the pellet size distribution will remain, but the yield will start going down. If the yield goes down, the recycle will start becoming more and more. So the surging problem may come once if your layering of your feed material onto the recycled pellet is not taken care of adequately. So theoretically, what I think is about 40 to 50% of your material should go in for the layering process, and the remaining 50% can go through your nucleation coalescence. Then we will be able to operate the plant with much more confidence and ease. Once these values proportions undergo changes, then there is either more quantity of pellets produced which are smaller in size, or suddenly the pellets are becoming bigger but not of strength, and the yield also is going down. So the size, distribution of pellets, strength of the pellets, and the yield of pellets, all these three will be a parameter dependent on the recycle load and the proportionate distribution of the initial, that is feed size coming, regular feed, in the process of nucleation and coalescence, and in the layering of the recycled pellets. There, if it is equitably distributed, then the plant operation can be considered to be under control. Okay, any variation, then we need to troubleshoot. Okay, so again explain. Okay, what we did was we went to a plant, sat down, then collected lot of information. Then we started using the soft computing methods and generate these kind of cyclic variations of the product, the recycle. Then we were trying to find out the product and recycle, that cyclic variation should be consistent. There should not be too many cycles, the time cycles required. So once they become steady, that means there are some n number of peaks before it becomes steady. Then that should remain there. If both the recycle and the product can reach this kind of a cyclic variation where after some time there is not much of fluctuations, then the system is under control. So we did that kind of thing. Due to paucity of time, I'm going through a little bit faster. This slide, please, you go down, go through. This only tells you how you need to collect the data, how you should train your soft computing tool like MLP or SVM, then generate these cyclic variation patterns of the product and recycle. Then this can be built into a computer program. Then it can be simulated. Then we can I will just complete in a few minutes. Okay. So this is the dynamic response of the process under different operating conditions in the plant itself. So we collected data, used our knowledge of the batch process, used the soft computing tool to generate this kind of variations and all. Then you can see the one at the top is the product, the one at the bottom is the recycle. they should be mirror images. If more products are coming, less recycle should be there. So if that kind of a pattern we start getting, then we know that we are understanding the process effectively and able to control the process better. Then we use a .NET simulation tool, a graphic user interface. Then we generated a final graphic user interface. There are many things in beforehand where the moment I keep feeding the data, then the calculations start taking place. Then this is the final one that will tell how the product is varying and how the recycle is varying. So this trend, once we know what should be the optimum, what should be the ideal, if we get as close a cyclic variation to that and if we can maintain that, then that means we have handled the industrial scale operation very well. So I have tried to put all the knowledge that I have gained over 4 decades, both on the fundamentals and the industrial practices, to give the listener an idea about how the R&D can be scaled up to control the industrial scale operation more effectively and more productively. Thanks for kind listening. Thank you very much.